Hi there, and this is Interpreting Graphs and Functions with Mr. Woolard's class. Everybody say hi. Yeah. Okay, so let's take a look now. So the idea here is we want to introduce the idea of linear versus non-linear functions. So a linear function has specific characteristics that help us to identify them. So linear functions have a consistent common difference, also called slope. Linear functions, when represented graphically, appear as a single straight line. So this is important to realize here, that it's a single straight line, not like a broken line. Oh, and my pointer's not working. That's not good. And linear functions as a single straight line, but vertical lines are excluded, because remember that a vertical line is not a function, because you'd have more than one. Josh, what are you doing? Okay. We have more than one output mapped to a single input. So as well, any continuous linear function can be converted to slope-intercept form. That's the form y equals mx plus b that we saw in grade 9. Or general form, cx plus dy is equal to e, also that we studied in grade 9. So a nonlinear function is simply any function which does not meet the characteristics of a linear function. Okay. So here we're asking the question, is this linear or non-linear? So let's take a look here. Now, remember that you can have discrete linear equations and continuous. So do these dots appear to fall on a single straight line? Yes. Yeah. Okay. These dots will fall on a single straight line. So this one is linear. Oh yeah. Okay. Glasses on makes all the difference. Okay. So now let's take a look here. Does this function represent a single straight line? No. No. No, it does not. These are two lines put together. So this is not linear. I think you guys are getting the hang of this. Okay. So now let's take a look at this one. This last guy, is that linear? Yep. Yes, because it's a single straight line. So this is linear. Okay, so let's try challenging ourselves with this next set. Okay, so again, linear, non-linear. This first one, linear or non-linear? Yeah, this is not linear, because it's got curves. Okay, next one. Is this linear or not linear? No. No. Nope. Nada. Nada. So again, not linear. Okay. Maybe we're seeing a pattern here. What about this one? Yeah, this is linear. Now, it doesn't matter that the points are spaced differently. All that matters is if the points lie on the same line. So this is linear. And it's a discrete linear, but it is still linear. So that's awesome. Okay, let's take a look now at our next guy. So we can also determine if a function is linear by both its table of values and its equations. So here's the things to look for. So for linear functions, the equations are polynomials with degree 1. So what that means is the variables do not have exponents other than 1. So you can't have like a squared variable. You can't have like a cubed variable. You can have your, sorry, say again?
Then it's quadratic.
That's right, that's right. If it's squared, it's quadratic. If it's cubed, then it's cubic. If it's to the fourth, then it's quartic. To the fifth, then it's quintic, and so on with Latin. So, and then here's the important part. Now, this is a big part of what we did in grade 9. So for every equal increase in the independent variable, the dependent variable increases by a consistent amount. And that's the idea of slope that we introduce in grade 9. So I want to show these three examples are all examples of linear functions. So let's take a look here. Is this part here on the left-hand side a polynomial of degree 1?
Yes.
Yeah. Is the thing on the right at least a polynomial? Yeah, 9's a polynomial. Right? It's just a monomial of degree 0. So overall, this has degree 1. So that's perfectly fine. So this middle one, we're going to pay close attention to here. So take a look here. When I go from 4 to 7, how much do I add? 3. When I go from 7 to 10, how much do I add? Okay, so what it says is, if I make the same increase in x, then I should have a consistent increase in y. So from 6 to 18, how much do I add? 12. Okay, and when I go from 18 to 30, how much do I add? 12. Excellent. So notice that when I add 3 and add 3, I add 12 and add 12. That's what we mean by consistent. If the difference in x is consistent, then the difference in y must also be consistent. So now, let me ask you this. To go from 10 to 11, how much is this?
1.
1. And from 11 to 12? And from 12 to 13. Okay, so now think about this. When I moved 3, I added 12 to my output. What do you think I do when I only move 1? Yeah, you got it. So how'd you get that? How'd you get 4? Yeah, exactly. So Jaden got it. So the idea here is that your slope is equal to your change in y divided by change in x. So Jaden saw that the change in y was 12, the change in x is 3, so the slope is 4. So if I only change by 1, then I have to add 4, and that's what we consistently do. And just to blow your guys' mind, take a look here. What's 10 plus 3? What's 10 plus 3? Okay, so if I added 3 here, I get 13. And what's 30 plus 12? 42. So it matches up perfectly. Okay? So this is what we mean. So this does represent a linear function. Okay? And using the slope equation from grade 9 is going to be a big part of what we're doing in the next unit. Okay? So it's not quite time to use slope yet, but it's going to be a major part of what we're taking a look at next. So let me get my little hand icon here. So now we're going to take a look at this set. So this is just the set of ordered pairs of some discrete linear function. So we're going to do the same thing here. So notice that here the x value is always increasing by 2. So 2 plus 4, 4 plus 2, 6 plus 2, and then from here I'm adding 1. So these guys will be different. So let's see here. So when I added 2 to get 4, what do I add to 7 to get 13? 6. Okay? And again, I add 6 to 13 to get 9. So far it's consistent. I add 2 again. I add 6 to get 25. So when I added the input by 2, I add the output by 6. If I add the output by 1, what will my new output change by? 3, because it's half of it, right? So again, we use the change in x divided by change in y. So now it's going to be, if I'm only changing by 1, I add 3 and add 3. So that's what we mean by a consistent change. Okay. So let's take a look. Hand icon. So let's take a look here at our next one. Okay. So this is our topic of interpreting graphs. So what I got here is I've got a distance versus time chart. So let me ask you this first. Which one of these is the independent variable, distance or time? What do we say? Which one is the horizontal axis? Time. Remember, the horizontal axis is always your independent variable. So time here, this is our independent variable. Which one is our dependent variable? Distance. Okay? So the independent, always horizontal. The dependent, always vertical. So what we want to do is we want to tell a story about this graph. We want to know what's happening. So what we have here is, for instance, I can tell the following story. That this is someone who starts out a certain distance from home and they get farther from home. Okay? Then during a period of time here, they don't move at all. Then they approach home very, very quickly, and then they slow their approach, and then finally after 20 seconds they get home. Okay? So the idea here is this is a positive slope. So hopefully this is something that's kind of coming back from grade 9. So you have positive slope. And if this is a positive slope, what kind of slope is this? A negative slope. Okay? So one thing that I like to do is you can think of your arms as giving you the positive and negative. So if you hold up your arms in front of you and make kind of like the roof of a house that like a 6-year-old drew, then your left arm is positive when you're looking at it, and your left arm is positive, your right arm is negative. So any slope that looks like this is positive, and any slope that looks like this is negative. So this is a negative slope, and this is a negative slope. This is a positive slope. So what is this slope if it's directly horizontal? What kind of slope is that? It's a slope of 0, right? It has 0 slope. Okay? Now, what would we call a vertical line? Does anyone recall what we call the slope of a vertical line? It's undefined because it's like it's infinite. Okay? So the slope of a vertical line is undefined, but the slope of your horizontal lines, these are 0. So let's take a look at another example. Okay. So what I want to do here is we're going to describe the motion represented by this function's graph. So again, we've got, this time it's speed, and is this our dependent or independent variable? Dependent. Okay, and time, dependent or independent? Independent. Okay, so let's ask this. So from A to B, if this is vertical speed, horizontal time, what's happening from point A to point B? Speed is increasing, right? Speed's increasing. Okay, what's happening from B to C? Yeah, the speed is staying the same. Okay, what's happening from C to D? Decelerating, right? So it's slowing down. What's happening from D to E? It's constant speed, but what is the speed? 0. So the person's like, so think about this. You're leaving home for work, you're driving in your car, you hit like a nice pace, and then you see a stoplight come up, right? So you slow down for the stoplight, you wait for the stoplight. So now you speed up again, okay? You reach a higher speed. Maybe you're angry that you hit the stoplight and you're speeding a little bit, and that's bad, so don't do that. So now you catch up to somebody, you have to decelerate to be able to go behind them. And then here again, you're at a constant speed, and then you decelerate again. So what we can do is we can take a look at the different sections, and we can talk about what's happening. So let me grab one of my thicker pens here. So we said from A to B, we're speeding up. Okay. So what did we say is happening between B and C? Well, it's a constant speed, right? So we have our constant speed. Okay, what's happening from C to D? Decelerating, using some good science terms, good physics terms. Using those good science terms again, what's happening between D and E? Constant speed, and what is that speed, sir? 0. So you are stationary. Stationary. If you're staying still, you're stationary. Okay, what happens between E and F? Speeding up. Let's use that science term, accelerating. Accelerate your breath. Okay. Between F and G, Josh, what's happening between F and G?
It's
constant speed. Okay. And between G and H, decelerating. Okay. Between H and I, constant speed. And then finally I and J. Decelerating. Okay. So let's take a look at our next guy. This is the last one for today. Yay! Okay, relations and functions. So sketch a graph with no scale for each of the following. So scale here is we're just talking about speed, we're just talking about time. It doesn't matter what their numbers are. So we're just going to talk about the general. Okay. Do I have any volunteers who want to come up and try drawing with this thing? Who want to try drawing for the speed of a bike when it goes downhill? Do you want to try? Yeah, Josh, you want to come? Yeah, it's easy. So I'm going to give you one of the big brushes so it's easier to see. Okay, so yeah, hold the pen. Okay?
Well, that's how you can draw so good.
Okay? So do you see here, so put the pen on the tablet there and trace it. So if you, that's okay. Okay? So now go up to draw. So here, I'm just going to